So these are some practice problems that will help us deal with the week 1 topics in the Algebra Remediation course, which goes through comparing and ordering real numbers, GCF and LCM, and simplifying square roots. So on to the first question. So of the list that you were given, basically what you need to do to determine the order that these need to go from least to greatest is get some in a common structure. So basically, the easiest way to do that is to get them all into decimals. And the easiest way to do that is on a calculator. Because 1/7 is 1 divided by 7, you can turn that into a decimal. 20%, basically, you just you get rid of the percentage point and move the decimal place 2 spaces to the left, and you get it into a regular decimal. You could do the square root of 0.5 and see what that is. The absolute value of negative 0.5 should be pretty easy to do, because all you're doing is taking an absolute value. So if you turn these all into decimals, these are the values that you get. And as you can see, looking at a number line, the 1/7, which is 0.14286, is the smallest of these. The 20% or 0.2 is next in line. The absolute value of negative 0.5, which is 0.5, is next. And then, of course, the square root of 0.5, which is 0.7071, is the biggest of these four. So basically, for this, from least to greatest, that is the order. Try another one like it. Now again, these have different notations. 2 of them are already in decimals. The fourth one's in a decimal, but it's also in scientific notation, so you have to evaluate that. And even if you're not familiar with scientific notation, you should know what 10 squared is and be able to multiply 1.2 times that. Negative 1/2, even if you don't know it as a decimal, you can still kind of guess where it should be in a realm of possible answers. But when I turn these all into decimals, the negative 1/2 is a negative 0.5, and 1.2 times 10 squared is actually 120. So when I post the 0.125, it's pretty much right there. And I'm scaling these going by, I think it's going by 20s. So negative 2.1 is going to be, on the other side of 0. Negative 1/2 is going to be right smack up against it with this scaling, but I know it's big. It's closer to 0 than negative 2.1, and of course 1.2 times 10 squared is going to be way over here. So if I'm ordering these from least to greatest, it goes negative 2.1, negative 1/2, 0.125, and 1.2 times 10 squared. So try this question now. So which integer is greater than negative 32 and less than negative 17? This question sometimes are asked because students often focus more on the numbers than they do on the negatives. And, basically negative 32 is smaller than negative 17. So, on the number line, they would be in this order here. And I'm looking for something that falls in that region that I have kind of highlighted there a bit more. So if I plot these according to where they are, negative 40 and negative 35 would be to the left of negative 32. Some people want to put them to the right. They're to the left. And negative 15 is to the right of negative 17. The only one that falls in between them is negative 20. So negative 20 is the correct answer. On to the next problem. So here you're asked to see which one of these number lines is the correct graphing or showing of these 5 numbers in the set given. So take a moment and pick which one it is. Again, to help you out, although these numbers are not very unreasonable, sometimes students will misinterpret the negative 7/2 and so forth. If I write these all as decimals to get them all on common ground, 3.5 is still 3.5. Negative 7/2 is negative 3.5. 1/2 is 0.5. Negative 2 is, of course, negative 2. And negative 1.5 is negative 1.5. And so I just have to go through and see which of these has all 5 of these correctly placed. So if I look at the 3.5 first, all of them had that one in the right place. So this doesn't exclude any of them yet. So right now, all 4 are still a possibility. And the same thing happens when I try to negative 3.5. All of them have that plotted correctly, too. When I get to the 0.5, 0.5 should be somewhere between 0 and 1. I can see that B, C, and D have them. A does not have any point between there, so I could automatically exclude A at this point. The next one, negative 2. Negative 2 is easy to plot, and I can see that of the ones that are left, only B and C have a point at negative 2. So now I'm down to B and C, and when I look at those, I'm looking for negative 1.5, which should be between negative 2 and negative 1. And that's where, but B has, C does not. So B is the correct choice of these 4 options here. Let's try the next question. So this gives you a whole bunch of different information. Some of it's actually more information than you actually need. I mean, you could probably get away with just having everything following the if and still be able to answer these questions. Because these numbers do make those 3 inequality statements true. And it's important to note, though, that we know that all the w, x, and y are negative, which means that z is the greatest of all of them. And in some cases, I'm going to be subtracting negative numbers here. So when I go through this list to see which of the statements are true, first I'm going to substitute. So z becomes 0, y becomes negative 1, x becomes negative 4. So I have 0 minus a negative 1 on the left. I have 0 minus a negative 4 on the right. And we all know that when I subtract a negative, it's the same thing as adding a positive. So the left is actually 0 plus 1, which is 1. And the right is actually 0 plus 4, which is 4. Which gives me a statement of 1 being greater than 4, which we know to be false. So the first statement's not true. All of them have z minus y, so the left-hand side for all these is going to be 1. On the left-hand side, I have negative 4 minus a negative 6. Well, negative 4 plus 6 is going to give me a 2, which makes this statement 1 is greater than 2, which is also false. For the third statement, 0 minus negative 1 is still going to be 1. 0 minus negative 6 is going to give me a 0 plus 6, which is give me a statement of 1 greater than 6, which we also know is false. And so, like by process of elimination, the 4th statement should be true. You should always double check it, though. The left-hand side still becomes 1. The right-hand side, I have negative 4 minus 0. And that gives me a statement that says 1 is greater than negative 4, which is a true statement. 1's positive. It has to be greater than any negative, so this is a true statement. On to the next question, which involves the greatest common factor. So when you look for the greatest common factor, the first thing you need to do is get the 2 things factored. So I'm going to take 357 and I'm going to factor it into 3 and 119. And 119 is a prime number, so I can't factor it any further than that. 339, I get 3 and 113 as my 2 factors, and 113 is a prime number. So when I look for the greatest common factor, I'm looking for the biggest, product of numbers that both of them have. And I can see that both of them have 3, and that's the only thing they really have in common. So the greatest common factor for this is 3. For this one now, 126 and 136, again, I'm going to start off by factoring the 2 numbers. So 126 factors into 6 and 21. The 6 factors into 2 and 3. The 21 factors into 3 and 7. All those numbers are now prime. So I can rewrite 126 as 2 times 3 squared times 7. The videos that you were shown often don't write them with the exponents, but a lot of textbooks do. So to give you kind of another perspective to see what that looks like. Because what you're going to be looking for oftentimes is the lowest exponent of each number if there's any of them in common. So for 136, I can factor that into 4 and 34. The 4 will factor into 2 and 2. The 34 will factor into 2 and 17. Which gives me that 136 equals 2 cubed times 17. Now when I look at these 2 numbers, they both have 2's in it. I mean the 3's in 126, the 7 in 126, and the 17 in 136, they're not in common. They both have 2's, And basically the highest power of 2 that both of them have, which basically means I'm looking for the lowest power of 2 between the two, is just 2. So for this this particular problem, the greatest common factor would be 2. Let's try another one. So again, for this, I'm going to factor the 660 and the 780. So when I factor the 660, and there's different ways you could factor them. So it's just making sure you end up with the same prime factors when all is said and done. So 660 can factor into 10 and 66, which can in turn, the 10 can factor into 2 and 5. The 66 can factor into 11 and 6. 11 is prime, 6 is not. So the 6 can be factored further into 2 and 3. So that means that 660 can be represented as 2 squared times 3 times 5 times 11. For 780, I can factor that into 10 and 78. The 10 will factor into 2 and 5. The 78 will factor into 6 and 13. And the 6 would factor into 2 and 3. So when I take all the prime numbers, 780 is going to be represented by 2 squared times 3 times 5 times 13. Now, when I look at between them, I'm looking for everything they have in common. So they have 2's in common. They both have 2 squares as well. So 2 squared is part of the greatest common factor. They both have 3's. So the multiplication of 3 is part of the greatest common factor. And 5's are being multiplied in both. So 5's are the greatest common factor. 11 in the 660 doesn't have any 11 in the 780, so it's not common. And neither is the 13 in the 780. So the greatest common factor is going to be 2 squared times 3 times 5, which is 60. And so that is the greatest common factor. Now you're going to look at the least common multiple, which a lot of students confuse with the greatest common factor because you start with the same thing. So be careful as you start this one. You're looking for the least common multiple, not the greatest common factor. So, like the other problems, we are going to start the same way. We're going to factor these. So, 111 will factor into 3 and 37. 37 is a prime number, so is 3, so that's about as far as I'm going to go for the 111. 54 will factor into 6 and 9. The 6 will factor into 2 and 3. The 9 will factor into 3 and 3, so 54 can be written as 2 times 3 cubed. And now what I'm looking for is the least common multiple. I'm looking for a number that 111 and 54 will both be factors of, but we want to make it the smallest possibility of those. So when I look at this, I'm looking for the highest power of each number that each one of them has. So, for instance, the 2, 54 has a 2, 111 doesn't have one. So 2 is going to be part of the least common multiple. I have 3 over here in a 111. I have 3 cubed in 54. So 3 cubed being in common is going to be part of the least common multiple. And the multiplication of 37, since it's in the 111, is going to be in the least common multiple too. So the least common multiple would be calculated by doing 2 times 3 cubed times 37, and that'll give you a total of 1,998. That is the least common multiple between these two numbers. Try it for the next one. So again, both of these, I'm going to factor them into prime numbers. So 98 is going to factor into 2 and 49. The 49 will factor into 7 and 7. So 98 I should say 98, have the right factorization, just had the wrong number there, is 2 times 7 squared. Whereas 28 would factor into 4 and 7, which would in turn factor into 2 times 2 for the 4. The 7's already prime. So 28, its prime factorization is 2 squared times 7. So when I look for the least common multiple, they both have 2's as part of their multiplication, but 28 has a higher power of 2. So that's going to be part of the least common multiple. They both have 7's in them, but this one has a higher power of 7, so that's going to be part of the least common multiple. So the least common multiple is going to be 2 squared times 7 squared, which is basically 4 times 49, which is 196. So one more attempt at least common multiple. Now for this, again, I'm going to factor both. 216 becomes 6 and 36. The 6 becomes 2 times 3. The 36 will be factored into 2 more 6s, which in turn get factored into 2 more 2-3 pairings. And so basically 216 can be written as 2 cubed times 3 cubed. 27, I can multiply it by 3 and 9, and I get 3 and 3 for 9. So 27 is 3 cubed. So when I look at these, 216 has a 2 cubed, while 27 doesn't have it. So this is going to become part of the least common multiple. They both have 3 cubed as part of it, so 3 cubed is definitely part of the least common multiple. And so the least common multiple ends up being the 2 cubed times 3 cubed, which we already know is 216. So it happens to be that 27 is a factor of 216. And so it's the least common multiple because 216 is obviously going to be a multiple of itself. It's a multiple of 1, you know, so. This kind of idea is used when you start simplifying square roots. So the next question is going to have you do that. So when you do this, you basically are trying to split up the number underneath the radical, which is another name for the square root symbol, into perfect squares and non-perfect squares. So, you know, I'm going to show it one way, but you'll see eventually we'll revert to using the factor tree again. I mean, 147 is 7 times 21. Neither one of those are perfect squares, but if I break down 21 a bit further, 21 is 7 times 3. As you can see, we have 7 times 7 here. Any number times itself it's basically being squared. So I can separate the two square roots as so, knowing that 7 times 7 is the same thing as 7 squared. So we have the first radical having a square root of a perfect square, whereas the second radical is the square root of a non-perfect square. When I square root 7 squared, I just end up with 7. So the final answer is 7 times the square root of 3. So try a similar process to answer the following. 968 has a good number of factors, so instead of me like hit or missing it, I'm just going to use a factor tree to get it into its prime factors. So 968 is a multiplication of 8 and 121. The 8 can be factored into 2 and 4. The 121 can be factored into 11 and 11. The only thing that's still not prime is 4, so that would be split into 2 and 2. So the prime factorization of 968 is 2 times 2 squared times 11 squared. Now, typically I would have written it as 2 cubed times 11 squared, but there's a very specific reason why I wrote it this way. And that's because, again, I'm trying to separate parts of this number that are perfect squares from those that are not. Because what I'm going to do for this is when I simplify this square root, I'm going to put the 2 squared times 11 squared in one radical. I'm going to put the 2 in the other radical, because 2 is not a perfect square, but 2 squared and 11 squared are. So I would basically have the square root of 2 squared times the square root of 11 squared times the square root of 2, which is 2 times 11 times the square root of 2, which becomes 22 times the square root of 2. And that's the square root of 968 in its simplest form. Let's try it again now with more multiplication going on. Now for this one here, I mean, we already have some things that are outside the radical, and I have some things that are inside radicals. So the numbers that are inside the radicals, the square root symbols, I'm going to factor them into prime factors to see what I have. So the 12 will eventually factor into 2 squared times 3. The 27 will eventually factor into 3 cubed. So when I look at this, I can see that, you know, when I rearrange this and replace the numbers in the radicals with their prime factors, this could be rewritten as 3 times 5, those are the numbers that were outside the radicals, times the square root of 2 squared times 3, which is the 12, and the 3 cubed. The 2 squared is a perfect square. The 3 and the 3 cubed are not, although 3 cubed does have a perfect square as a part of it. If I multiply these two radicals together they would combine as one radical, and the 3 times 3 cubed would become 3 to the fourth. 3 to the fourth is a perfect square since it has an even exponent. So now the thing is, if you're leaving them in terms of their powers, you're not going to square root the 3 and the 4 or do anything like that. The only thing that the square root is going to do is affect the exponent. If you choose to write these as 4 and whatever 3 to the fourth is, which is escaping me right now, 81, then that's fine too. It's just then you can square root the number that you have. But if you're handling it as powers, remember that all the square root's going to do is basically take half of the power that you're seeing. So for this case here, this becomes 15 times 2 times 3 squared, which becomes 15 times 2 times 9, which is 270. Now let's throw some variables into the mix. So for this, I'm going to handle the exponents much like I handled some of the numbers in the previous one. I'm also going to handle the coefficient of 28 in the same way I handled the numbers as well. So now you're not going to see me factor 28 completely because I do know it's divisible by 4, and 4 is a perfect square. And when I carry through that factoring, I get 4 times 7, where 7's a prime number. So I know that 7's a prime number, 4 is a perfect square. So that's a good separation. The x to the 7th I split into x to the 6th times x because, again, x to the 6th is a perfect square since it's an even exponent. Whereas the x, having just an exponent of 1, which I usually don't write, is not a perfect square since it's an odd exponent. And x to the 6th is the biggest exponent of x I could take out of x to the 7th. So this allows me to separate this into 4x to the 6th power times the square root of 7x. The square root of 4x to the 6th technically would become 2. The square root of 4 is 2. The square root of x to the 6th is technically the absolute value of x cubed because when I do these square roots, we're assuming it's the principal square root, and the principal square root always returns a positive answer. X, however, could possibly be negative, because we don't know what x is. And if I raise it to a 6th power, it would change it into a positive number. And if I square rooted that, I'm not going to get back the original number because if it was negative, I'd get back its positive counterpart, hence the absolute value. So technically, that's what I'm supposed to do. However, as I look at this further, for the original, which had an x to the 7th, and this part of the answer, for these to exist, x can't be negative because that would make what's underneath the radicals negative, and I wouldn't be able to evaluate them because if I'm looking at real numbers only, the square root of a negative number doesn't exist. So if x is greater than or equal to 0, because that has to be that case to exist, then I don't need the absolute value anymore because then I know that x is 0 or more, which makes it positive, or at least makes it non-negative, and therefore I don't need the absolute value anymore. So as long as I can come up with that, then I can oftentimes get rid of the absolute value symbol for this. When I start dealing with other roots and other powers, then I sometimes have to keep that absolute value around. So try your luck on the next one. Now for this one here, again, I have multiplications going on. I have numbers underneath radicals. I have x's underneath radicals. So I'm going to start off by factoring these. Now there's no perfect squares that factor out of 15 or 35. So I'm just going to give them their prime factorizations. So the 2 times the square root of 15x cubed will become the 2 times the square root of 3 times 5 times x squared times x. And there's a very specific reason why I'm keeping the x squared and x the way that is. And the 5 times the square root of 35x squared becomes the square root of 5 times 7 times x squared. So when I rearrange this, the 2 times 5 I'm going to put together because they're both numbers that were outside of the radical, so they would multiply together. What I'm doing here is I notice that the 3 is not a perfect square. There's no other times 3 throughout this whole thing. So the 3 is going to get put into the second radical, is where I usually put the stuff I have that is not a perfect square. The 5s, however, they both have 5, so 5 times 5 would be a perfect square. It's 5 squared. So I put the 5 times 5 under here. This x squared I put under here. This x squared I put under here. This x I put under here. And of course, since the 7 is only in this radical and it's not a perfect square, it comes down to the second radical over here. So I have coefficients. I have things that will become perfect squares. And I have basically things that will not become perfect squares. And so when I work this out a bit further and simplify, the 2 times 5 becomes 10. The 5 times 5 becomes 5 squared. The x squared times x squared becomes x to the 4th. And I have the square root of 21x being simplified over here, so that when I finish this up, I end up with 10 times 5 times x squared out here, which means that I'm going to have 50x squared square root of 21x. I don't need to put an absolute value around the x squared, because whether it's positive or negative, even if I mean, granted, I would still have to probably make the case that x would be greater than or equal to 0 here, because if it weren't, then this original radical up here wouldn't be able to be done because it would be negative, because if I cube a negative, it's going to be negative. So I wouldn't be able to do that, and I wouldn't be able to do this one down here if x is negative. However, even if I would allow that to not be necessarily the case, if x could be negative, the fact that I'm squaring the x would preclude me from having, a negative number here anyway. So as a result, the x squared is already positive. I don't really need to put absolute values around it, so I don't really have to go through as much information about the domain as I did in the previous one. And so one last example before we call it quits to this. Here you go. So again, I'm going to do some factoring underneath the radicals. And I'm going to do some rearranging. Now again, I took some shortcuts with the factoring of this because I said it's 2 times 3 squared. I could have left it as 9, knowing 9 is a perfect square, but I just write it as 3 squared. As I look at this, though, and start rearranging, the 3 times 4 are going to be grouped together because they're outside the radicals. They will be multiplied. I have a 2 here and a 2 here, so when I multiply these two radicals together, they would combine underneath the same radical, and 2 times 2 is 2 squared, so I'm going to keep it. The 3 squared, that stays, it's a perfect square. This x squared stays. This x times this x becomes x squared as well, so that's where this second x squared comes from. This y and this y multiply together, giving me a y squared, so that's where this y squared comes from. And of course, this y squared down here goes in there as well. So basically, all the components underneath the radicals are either a perfect square as they are, or when I multiply it to a like element in the other radical, they form a perfect square. So what I end up having here when I simplify this a bit further is that I have 12 times the square root of 2 squared times 3 squared times x to the 4th times y to the 4th, which becomes 12 times 2 times 3 times x squared times y squared, which becomes 72x squared y squared. Now again, I should probably make a condition that x and y have to be greater than or equal to 0 for these two originals to work, because since I have nothing but odd exponents in the originals, if I have any of those being negative, that could create a situation where radicals can't happen. And it could be the case that if both x and y are negative, then at the same time, then I can still do them because negative times negatives are positive. So it would basically be me having to eliminate possibilities when x is negative and y is positive and vice versa. But we don't have to get into that too much here, since I do end up with an x squared and y squared. I don't need the absolute values because they'll be positive without me using an absolute value to do it. And that's the end of this. So tally up how you did and compare it to what these answers are to get an idea of where you are. go over some of these again and the concepts again before you take the quiz. And good luck on the quiz.